record this because I had an online student ask for some more, and also another student asked for it. So um, we are going to first review 10.2, 10.3 correlation and um, linear regression. And I did not show you how to see it on your graphing calculator. So we are going to do that with this problem. One of the things I kept saying, oh, I got to do that. So let's bring up your calculator here. So this particular problem is seeing if there is a correlation between PSAT and SAT scores. And it's given us both scores. So we are going to take a look at this. Now mine, I have to go and turn on my diagnostic every time. So bear with me, because if not, it won't calculate my Pearson R. So every time the calculator goes off, it turns it off. It should not on yours. Okay. So our X, or our independent variable, is going to be our PSAT scores, and our dependent or Y variable is going to be our SAT scores. And just like we've been doing all semester, we're going to go right into our stat and edit our lists. So I'm going to clear what I have. And enter those scores. So I have 8 pieces of data there. We have to know that so that we can look at our scores, our Pearson moment, decide if the linear regression is a good linear regression, good model or not. We're going to go back and get out of our data. We're going to go to stat. We're going to go to calculate, and we're going to ask for number 4, a linear regression. Again, my X list is L1, Y list is L2. My frequency would be 1. I don't have to put that in. And then this is where we are telling it to store the equation it comes up with in our calculator, so we can actually see the equation on the line graphed on the calculator. That's why we do this part. And again, that part is vars, cursoring over to y vars, choose number 1 function, y1, and then go down and enter. So the equation is y is equal to 4.562 plus 1313.719. That's my equation. The R value is 0.543. And I'm going to go to my table. And I have to go with n being 8. And we're going to do this at an alpha of 0.05. So my number there is, my critical number, critical value is 0.707. 0.707. My R here is 0.543. Is that a good or not a good model? Trying to picture it, right? What should we always do? Draw that picture. So true, so true. So that's a quick, got to see it. I agree. You know, I've been preaching that since the very beginning, right? Draw the picture. So if I have a line, remember that if it were a perfect model being that every single data point was absolutely on that line, that would be a perfect model. It could be with an R being -1, or it could be with an R being +1. Okay, my critical values is 0.707. So 0.707, I'm going to say is about here, but I also have to go -0.707, correct? Remember, the closer I get to +1 or to -1, that tells me there that it's a good model. Okay, and then it's not, because my R value, forgot that part, see? So good thing we're reviewing. So my R value came up to be 0.543. So 0.543 is inside that, right? So it's not a good model. Remember that not a good model at the ends are the good model. You were picturing the curve? Yeah, it's within the curve. And this one is over here would be a good model. So this one is not a good model, okay? That's just our test. But I want to use this so that we can, again, see it on our calculator. So if you bring up your calculator, go to y equals. In y equals, it automatically took this equation that it calculated and pasted it into y1. That's why we did vars, y vars, function, and y1. We told it to plot. We told it paste it there because I don't want to have to input it. I'm being a little lazy, right? Okay? So we could right now look at our graph. However, this goes back to the algebra part. My y-intercept is what? 13, 13. My calculator is probably set at the standard of 10 to -10. So it's, if I hit, I'm not going to see anything. I'm not going to see anything at all. So we have to figure out where we need to put our windows. One way is to look at the slope and look at the y-intercept. The slope is positive. That means it's getting bigger. So y has to, the minimum of y is going to be there is 13, 13. So I know I'm going to have to make it big. The other thing is to remember what is my independent and my dependent variable. My independent is what? My x, my L1. What did I put on L1? Look at these values. My PST test. So I think probably the highest was about 206. Okay. So I'm thinking, okay, on my X, I need to be from 0 to 225, 250. I always want to go bigger and below, okay? And then when I looked at these, when I had my Y or my L2, what's the biggest one there? 20, close to 2400. So I want to go above that, okay? But I also like to see my axes. I also like to see my axes. So, and there's no perfect science or perfect way to set that window. That's how you're going to gauge it, by looking at your data. So I'm going to go into where it says window, because my X has to go up to about 240. And right now it's set for -10. I'm going to make it even lower. Again, I like to see the axis. You don't have to see the axis. It's just something I like to see. So I'm going to set it at, say, 40. And my positive, I'm going to put it at 240. Now, look at that little teeny calculator window that you have. And right now on my X, I'm going from negative 40 to 240. If I leave it like that, where it says scale of being 1, it's going to put a tick mark at every single point. So I'm going to have 280 tick marks in that little calculator. So that's just not going to suffice, is it? So I want to change my scale. I could change it by 20s, 10s, whatever. I'm just going to change it right now to 10s, see what that looks like. And again, there's no perfect science to it. You're just making the best educated guess based upon what you know about your data and what it's representing. So when I cursor down now to my Y, it's going to go from 1,300 something all the way up to what? 2,400 at least, and we want to go above. So let's say that we're going to make our Y minimum negative 100. And I'm going to go up to 2,500. And again, my Y scale there, I'm probably going to make my scale there 100. So now I'm at least going to see something. So let's hit graph. And now I can see my line. The line is the linear regression. It is the model. It's the model that the calculator built based upon those data points. Okay? I don't see any data points though, but this is how we're going to see data points. You're going to go to second, stat plot. And number 1, see where it says plot 1 off? We're going to choose number 1. And we're going to click on, hit enter while it's blinking. Here's where I can change the type of graph. The type of graph I do want is this first one. It's the scatter plot, and that's exactly what I want. And it's coming from my data located on L1 and my data located on L2. Everybody okay? Second, Y. I'm going to turn that on. Then go ahead and hit your graph now. And now you'll see the model, the line, but you'll also see my individual data plots, those points right there. Okay? Get it? Okay. Makes sense? Okay. So that's not bad, right? Okay. And it's good to review that information, right? So we already answered, is there sufficient evidence to conclude that there's a linear correlation? No. Is there anything wrong or questionable about the data, and what would it be if there is? Self-reported. Self-reported. Okay. So while we're in that mode, sure. Oh, okay. So altitude and temperature. Listed are the altitudes in thousands of feet and outside air temperatures in Fahrenheit recorded by the author during a Delta flight 1053 from New Orleans to Atlanta. So we're going to, excuse me, we're going to go ahead and do this analysis, build our model, see if it is a good model or not. And I want you to look at it on your calculator. You don't have this one? Okay. Ugh. I'll make sure I post the notes. Are you able to see what the numbers are? Okay. I'm going to press pause on here so that while we're inputting everything. Okay, so I have put my data in L1 and L2. I'm going to go back to stat. I'm going to ask it to calculate, and I want it to find my linear regression number 4, L1, L2. And again, I'm going to go ahead and put it into my calculator so I can take a look at the graph. That's what makes it go, is that Y1, and enter. And I find that my results are that y is equal to negative 3.684 times x plus 72.498. That would be my linear model, my regression equation. My R value is negative 0.9968 or 0.997. I know that I don't even need to look at this blue chart because it's so close to -1, but we will just for the practice of it. And if I were testing at an alpha of 0.05, the number of pieces of data I put in there were 7, and that will be 0.754. And of course, negative 0.998 is much less than negative 0.754. So yes, it is a good model. Okay, everybody cool on that? All right, so let's just make sure and we'll see what the plot looks like. It's a good practice because, again, we have different data than I had last time, much different data. Remember, we were up to 2400 on the Y scale last time. This time on my X, my L1, goes from 3 to 33. So maybe I want to put in from -5 to 35. Okay, and my temperatures go from a positive 57 degrees to a negative 54 degrees. So I'll probably go from negative 60 to positive 60. I could have done from negative 100 to positive 100. So let's go into our window and change these settings. I don't even remember what I said I was going to put in there. So X max being, we'll go 40. For my scale this time, I can select 5. I could probably get away with 1, but 5 makes sense. Then my Y min, okay, it's already set at -100. I'll leave it at that, and I'll put it at positive 100. But I don't want my scale to be 100, maybe 10. And again, I'm just telling the calculator the size of the window so I can see my data and I can see that line. Okay? Once I have that, go ahead and hit graph. That's what I expected to see. I expected to see a negative slope, right? Going downhill from left to right because my slope was negative, right? So it was going to go downhill. And doesn't that make sense? Okay. How to get the points on there again? Right now, my stat plot is actually on, but I would go to second, y equals, above y equals is stat plot, and make sure that number 1, right there, you'll go to on, click on, make sure it's the scatter plot type, and L1, L2 is your list, and you hit your graph. Okay. So I can actually see my data points and I can see my line. And look how close those data points are to that line. And that's what we expected because my R was -0.997. That is so close to -1. It's so close to absolutely being perfect, right? Okay. Does that make sense? Is that better? So everybody's going to do very well on that part of the test, right? That part, yes, okay. Okay, excellent. Let me pause this again. Okay, so back to problems from 8.3 and 8.4. One that we haven't done yet is number 17 on tennis instant replay. So the Hawkeye electronic system is used in tennis for displaying an instant replay that shows whether a ball is in bounds or out of bounds so players can challenge calls made by referees. In the most recent US Open, singles players made 611 challenges and 172 of them were successful with the call overturned. Use a .01 significance level to test the claim that fewer than one-third of the challenges are successful. What do the results suggest about the ability of players to see calls better than referees? So let's add a page here. When I'm doing a hypothesis test problem, I'm going to go step by step by step by step. Without doing that, you're going to get yourself lost. My very first step is going to be to state the claim. So if you go back and read that problem and state the claim, let me see if I have the problem. You have an extra one? Thanks. That way it'll be easier for me than going back and forth to the screen. The claim, it says to test the claim that fewer than one-third of the challenges are successful. How am I going to write that claim in symbolic? First, is it a proportion or is it a mean? It's a proportion. And how do I know that? Because it says what? One-third. Okay, and it's given me data of this many out of this many. Those are all clues that it's a proportion. So the claim is that the proportion P, there's our P's, remember we have all kinds of P's going on. My proportion is what? Less than one-third. So that's my claim. Once I have my claim, I'm then ready to write my null hypothesis. This one is a no-brainer, right? Because my null hypothesis can and only have equality. So I'm going to say my claim, my null hypothesis is P is equal to one-third. Okay? Now that I know my claim and my null hypothesis, I can write my alternative alternate. And what is that one going to be? P is less than one-third. And the reason that from my claim to this is exactly the same is because there was no equality in my claim. Remember the chart I gave you, right? Okay. Now, what is my next step? Test statistic, right? So I've got to figure out my test statistic. What do I mean by that? Am I using Z or am I using T and Y? Z, because it is a proportion. Okay? My P hat, where's my problem? P hat, what does P hat mean? Predicted, right? Based upon this, P hat. 17, it says they were successful 172 out of 611, correct? What does that come to? 0.282. 0.282 is p hat. And I'm looking for my test statistic. So now what? .282. If p is equal to it, my claim is less than. Is this a one-tailed or a two-tailed test? It is a one-tailed test, isn't it? Okay. So I'm going to put 1/3, right? And what's 1/3? That's my claim. What did I come up with? 0.282, right? That's going to be down here, correct? And I'm using Z. Let's go into your calculator. Oh, that's for my mean. So I found my Z, yes? There's a formula as well. If we find our Z, what's my formula say? It's p hat minus p divided by the square root of p times q over n. Is that right? Okay. P hat is 0.282 minus 0.333 divided by the square root of, what's by p? 0.333 times q then would be 0.667, all divided by n, 611. Somebody tell me. You shouldn't be putting these there. Be confusing you putting those there. Somebody tell me what they calculated Z to be. It's going to be negative. Negative 2.675. Anybody agree? Okay, good. So that's my Z score. I now need to decide my area, my P value, right? Okay, so when I have a T of negative 2.675, I want to know what this area is. That's P value, correct? How am I going to find that p-value? Got a couple ways, right? I can go to my z-score chart, or I can go to my calculator and go second distribution, my normal curve. I have to put my lower in. What's my lower on this one going to be? Look at the picture. I went from way out here, right, of negative 99999 up to negative 2.675. My upper will be negative 2.675. And this becomes my p-value. You know I'm going to ask you for everything, right? So now I want to check. What is the z that I'm checking against? I found my z for my data. My z is what? 0.01 significance level, right? It's a 0.01 significance level. So if I did 0.01 significance level, let's get green here. That would be, that's my area right there, and I'm going to find my z. You could do it by memory, or you can do it in your calculator. What would I do on my calculator? Inverse norm. Second distribution, inverse norm, 0.01. And it's going to tell me negative 2.33. 2.33. So, to decide if I am going to, what do I do? Oh, I forgot the negative sign. Thank you. To decide whether or not I'm going to reject or fail to reject the null hypothesis, if I'm going by my z, I'm going to say, hey, is negative 2.675 less than negative 2.33? Of course, the answer is yes. So it is, and because it is, then what do? I reject the null hypothesis. I can also use my p-value test. We found out that our p-value is 0.004, and what I'm going to look at that is 0.004. Is it, this is the p-value test, is 0.004 less than 0.01? Yes, therefore reject the null hypothesis. Okay, does that make sense? Getting that refresher helps. Okay, well, now I'm almost finished, correct? I have to write my conclusion. And to write your conclusion, you're going to go to your little chart, right? Everybody has their charts. I have some more in here, I think. Maybe I'll give it to you. How do I read the chart? The first thing is I've got to decide if the claim had equality or not. Did it? No. Since it did not, I'm going to go down to the second little bullet there. Do you reject the null hypothesis? Of course, yes, we did. And because of that, we're going to say the sample data support the claim. That less than 1/3 would be my problem. Less than 1/3 of challenges are successful. So from beginning to end. Okay. Better. Every time you do one, it gets a little bit better, right? And I can't guide you on the test except for putting those things down, right? That's super helpful. Good. Good. Okay. So you don't miss anything, right? Because you know you're going to get parts for each thing that you do. I don't think we did number 18 either. Perception and reality. That would be a good one to do and review because of the test itself. Okay. And I definitely want to do one where we go mean. So let's look at this one. In a presidential election, 308 out of 611 voters surveyed said that they voted for the candidate who won. Based on data from a research group, use a 0.10 significance level to test the claim that among all voters, the percentage who believe that they voted for the winning candidate is equal to 43%, which is the actual percentage of voters for the winning candidate. What does the result suggest about voter perception? Is it a proportion or a mean? It is a proportion. Okay, let's get another page going here. First thing I want to do is write my claim. What's the claim? We already said it's a proportion, so I'm going to use a P. Let me tell me the claim. You're not looking at the paper. The percentage who believe that they voted for the winning candidate is equal to 43%. So my claim is P is equal to 0.43. Okay. My null hypothesis can only be equal, correct? My alternative is that P is not equal to 0.43. So in this case, I don't have a one-tailed test. I have a two-tailed test. Okay. My significance level is 0.10. I'm just taking it right off the paper. Yes. My data says that 308 out of 611 voters surveyed and that they voted for the candidate who won. And if you take 308 divided by 611, .504. Okay. I'm using a proportion. So using a proportion, am I using Z or T? Z. So that's P hat minus P divided by the square root of P times Q divided by N. P hat is going to be 0.504. P is 0.43 divided by the square root of 0.43 times 0.57 divided by 611. So if you can tell me what you got for a calculation of Z. We're going to have a positive Z. 2.69. 3.69. 3.69. That's my Z value. That's my test statistic. Tell me what my P value will be for this data. 3.69. Think about that. If I have my curve, my Z is 3.69. That means this little teeny speck out here, right? And how am I going to find that little teeny speck out there? That's the area under the curve, right? So, yes, I'll be glad to I'll give you everything. Yep. So I'm going to go second, distribution, normal curve. My low end this time is 3.69. My upper is 99999. And I'm going to come down and paste. And I'm going to find, wow, good. I'm glad it did that. So I can explain that again. Look at that. It's just floating wherever it wants to float instead of where I want it to float. Okay. So it says down here, this number is my p-value. What does that mean? So that -4 means it becomes a smaller number, and I'm going to move that decimal point 4 places. So that translates then to be 0.000112. That's my p-value. Scientific notation. Okay. Exactly. And even when I got that Z is extremely high. We can go, I know I'm going to reject this null hypothesis, right? But we'll go through the whole thing because on your test, you're going to have to show me why did you reject it. And I want you to test it both by the Z. Reject. Have you seen this number? So remember, we're doing a two-tailed test, correct? Okay. The two-tailed test, it's going to split them in half, correct? 0.1 split into the two tails is 0.05. So I can get my Z for that. I remember what that is. No, that's 1.96. I can't remember now. 1.96. So negative 1.96 and positive 1.64. I'm glad somebody's checking it. 64 and 1.64. That's my test critical values for Z. So I'm going to decide whether to reject or fail to reject because I'm going to look at my Z test. The Z that we calculated, 3.69, and I'm going to compare that to 1.64, and obviously 3.69 is greater than. In other words, it's going to come way out here to the end, right? To do my p-value test, I'm going to compare 0.10, and I'm going to compare it to not 0.000112. It's a two-tailed test, so I have to remember to what? Multiply by 2 times 2, which is going to be 0.000224. So I'm going to compare that. And obviously, this is greater than this. So both of them say reject the null hypothesis. Okay? And lastly, it has equality in it to start, right? So did we reject? Yes. So we're going to state what? There is sufficient evidence to warrant rejection of the claim. That 43% of voters vote for the winning candidate. Okay. And then let's go to another. I think we did the Oscar winning actress. I can't speak. Um, okay, let's do number 15. So is this diet practical? When 40 people use the Weight Watchers diet for 1 year, their mean weight loss was 3.0 pounds with a standard deviation of 4.9 pounds. That's based on their data from comparison of all these different diets. Use a 0.01 significance level to test the claim that the mean weight loss is greater than 0. Based on these results, does the diet appear to be effective? Does the diet appear to have practical significance? So I'm just going to go ahead and add another page here. You guys have that problem, right? Okay. First thing we're going to start with. What is my claim? We're using the level, we're testing the significance level of 0.01 to test the claim that the mean weight loss is greater than 0. The mean is greater than 0. Mu is greater than 0. Okay? My null hypothesis is going to be what? Mu is equal to 0. Okay? My alternate hypothesis, same as the claim in this case, that mu is greater than 0. And I'm going to make it the same because it doesn't have equality in the first part of the claim. There was no equality there. Okay? Our data showed what? That mu is equal to 3.0. The standard deviation, it's the standard deviation of that particular group. So it is the sample standard deviation. It's not of the population. It's the sample standard deviation of 4.9 pounds. Okay. So I have to decide on my test statistic. I'm going to use T, absolutely. Why am I using T? Yes, first off, it's a mean. And then I do not have this population standard deviation. I don't know what that population standard deviation is, so I have to use my t-test. Okay? So to find my t, minus mu all over so we're going to write what we're writing. If, in fact, my pen works, what is our sample mean? Our sample mean is 3.0 pounds. Subtract mu. Mu is 0. We're going to divide that by the standard deviation of the sample, which is 4.9, but that has to be divided by the square root of n, and n was 40. So calculate your t. I forget what we're testing at, an alpha of 0.01. Yes. What do you get for your t? I got a couple people going no. 2.87, 3.87. What does your gut tell you already? Yeah, I'm going to end up rejecting it. But let's keep going and follow the problem through, okay? There's my t. Remember, you got it? Okay. Remember, too, that you can go to your calculator, and you have to get your calculator going for this because you have to have, remember, the curve is different and to find your criticals. So let's go to stat, cursor over to test. We're going to do number 2, which is a t-test. Again, this is where either I'm going to put data in or I'm going to just give it the stats. So in this case, I'm just giving it the stats because I don't have individual people that I put in L1 and L2. That would be my data. So I'm going to choose stats. I'm going to cursor down. Mu is 0. My X bar is 3.0. I'm going to cursor down. The standard deviation of the sample, SX, is 4.9. Cursoring down, N is 40. Is this a one-tailed or a two-tailed test? It is a one-tailed test, isn't it? And the test, I'm going to go back to what it says. It's that mu is greater than 0, correct? So on my calculator, I have to indicate that. Mu is what? Greater. So I'm going to cursor down and go over to greater than. Whoops, I didn't hit enter. Guess what? We did it right. T is 3.87. My p-value is what? For this particular curve at 3.87, the t of 3.87. We don't have a chart for our t's. So let's pull this out for the window, put it down here, which it didn't do. And again, my p-value with that -4 means I'm moving my decimal 4 places, so I'm going to have 0.0002. Yeah, we're going to end up rejecting, aren't we? Where do we find our t values? Remember where we're going to find our t values? They're going to come from our pink sheet for the t distribution critical values. The degrees of freedom, we had 40, so 40 minus 1 would be 39. Is this a one-tailed test? Yes. In my one tail, I have what? 0.01. So 0.01 in one tail. Did everybody see that's 2.462? 2.462. Oh, gosh. I am so dyslexic. It is pathetic. I really do cover it well most times. So my critical t value, I shouldn't say value, I want t, my critical t is it won't let me write, 426. Okay. So my alpha level was again 0.01. So I'm going to say that given that our t is 3.872, and I'm going to compare it to the critical t value of 2.426, obviously it's greater than, yes? And then when I talk about my p value is 0.002, and I'm going to compare that to this alpha significance level of 0.01, and of course this is much less. So both of those tell me to reject the null hypothesis. Okay? The null hypothesis was what? That mu is equal to 0. Okay? So given that particular problem, we're going to then use our chart. Was there equality in the claim? No. So since there's no equality in the claim, and then we do what? Reject. So the sample data support the claim. That the mean weight loss is more than 0. Okay. So now we did all that work, and we're going to go back to the problem because there's another question that says, does the diet appear to have practical significance? Danielle shaking her head no. Anybody else? How long do those people diet? A full year, and the average mean weight loss was 3 pounds. So does it have significant? No, not practical significance. Okay. You can do that without dieting. I can do that just by having too much salt and then getting lots of water in me. Right? Okay. All right.